Dear students, this is our 14th lecture on medicinal chemistry and third lecture on antipyretic drugs. In this lecture, we will discuss synthesis of some commonly used non-steroidal anti-inflammatory drugs, which we call as NSAIDs. In the first two lectures on antipyretic drugs, we have discussed about various types of NSAIDs and how they act in the body, that is mechanism of action of some of the common NSAIDs. Then in the second lecture, we have discussed about what are anti-gout agents and how they act because of certain deficiencies in the body which are created due to accumulation of uric acid. The gout is there in the body, and what are the agents which are used to remove that gout in the body, that is anti-gout agents. Now, in this lecture, third lecture, we will discuss the commercial synthesis of some commonly used non-steroidal anti-inflammatory agents. First of that category is ibuprofen. Uh, you might have used many times this salt, that is ibuprofen, for different types of infections in your body, which causes the inflammation. And to remove that inflammation, these anti-inflammatory agents, non-steroidal anti-inflammatory agents, they are used. And ibuprofen is one of them. As far as traditional industrial synthesis of this ibuprofen is concerned, this is synthesized from secondary butyl benzene, and this has been patented by Boots Company of England in 1960s. And the synthesis of ibuprofen through this process, that is traditional industrial synthesis, is a six-step process which starts with this secondary butyl benzene when reacted with acetic anhydride in presence of anhydrous aluminum chloride. Basically, Friedel-Crafts acylation will take place at the para position, and we will get 4 acylated butyl benzene as the product. And when this acylated butyl benzene is reacted with chloroethyl acetate in presence of base, this keto function group will be converted into epoxide ring with this carbon of the chloroethyl acetate acting as an anion and attacking this carbon, and then removal of halogen will lead to the formation of this type of epoxide. And then hydrolysis of this epoxide, opening of this ring, then lead to the formation of these types of terminal aldehydes. In the next step, this terminal aldehyde will react with the hydroxylamine, and condensation of amines with aldehydes or ketone leads to the formation of oximes. So the oxime of this aldehyde will be formed, and then this oxime is oxidized to the nitrile derivative through oxidizing agents, and then hydrolysis of this cyanide will get it converted into carboxylic acid to give us ibuprofen as the product. So this is how in a simple 6-step process butyl benzene is converted into ibuprofen. And in subsequent years, it was found that this industrial process is not a environmental friendly process. So therefore, a green synthesis was investigated, and that was patented by BHC company. And this is basically a three-step process instead of six-step process which was given by the Boots company. Now here the starting material is same as we have seen in case of traditional industrial synthesis, and here in the same way acetylation is done with acetic anhydride, and instead of anhydrous aluminum chloride we are using HF as the catalyst. Then if we will get the same product as we got in case of traditional industrial process. But the next product is different. Here reduction of this keto group is done with Ran-nickel. Hydrogenation is done, so this ketone is converted into alcohol functional group. So the respective alcohol is formed, and when this alcohol is reacted with carbon monoxide on palladium, this is converted into ibuprofen. So this greener synthesis is far better environmental friendly, and it is a short process also, whereby we can get our product in 3 steps. The next is ibufanic. Ibufanic is again synthesized from secondary butyl benzene via Friedel-Crafts acylation. So first step is same as we have seen in case of ibuprofen. Then in the next step, this keto functional group is then reacted with the sulfur in presence of morpholine, and this is called as Willdorf-Kindler oxidation. This is converted into thioamides. So these types of thioamides they are formed, and these thioamides on hydrolysis, basic hydrolysis in presence of phase transfer catalyst at high temperature of the order of 100 degrees centigrade, or in the presence of sulfuric acid simply, they are converted into the corresponding carboxylic acid. So this is how ibufanic can be synthesized from secondary butyl benzene. Then next NSAID is naproxen. Naproxen is also commonly used non-steroidal anti-inflammatory agent, and this has been industrially produced by company Syntex, starting from this starting material 2-naphthol. In the first step, bromination of this 2-naphthol take place, so we will get 1,6-dibromo naphthalene 2-ol as the product. So 2-naphthol will be converted into dibromo derivative of this type through bromination, and when this dibromo naphthalene derivative is reacted with sodium sulfide, then selectively one of the bromide is removed, whereas 6-bromo remains. So 6-bromo naphthalene 2-ol is formed through reaction with sodium sulfide. Then this reacts with alkyl halide. Methyl chloride is used for O-methylation of this hydroxyl group, and 6-bromo naphthalene 2-ol is converted into 2-bromo 6-methoxy naphthalene. So basically O-alkylation take place, or we can say O-methylation take place in this step. Then this is reacted with Grignard reagent. This magnesium bromide derivative in presence of magnesium metal reacts with this bromine and carbon-carbon bond formation take place. We can say a coupling reaction take place between this and this, and we will get a racemic mixture of this naphthalene propionic acid derivative is formed. And then this racemic mixture is resolved by using N-alkyl glucamine as the resoluting agent. Then this is called as Pope-Peach method, and we can get S-naproxen by having 95% enantiomeric access. This S-naproxen is the biologically active compound which act as NSAID, whereas R enantiomer is not active as NSAID. So this is how we can, through resolution, we can obtain pure enantiomeric naproxen as a drug. Then is next is phenoprofen. Phenoprofen is synthesized through 5-step process where we start with the reaction of bromobenzene with 3-hydroxyacetophenone. So when these two reactants, they are reacted with copper metal in presence of this potassium carbonate base, basically here H from here and Br from here will be removed, and we will get 3-phenoxy acetophenone as derivative. So this diaryl ether derivative is formed. Then this diphenyl ether ketone is undergoes sodium borohydride reaction. We know that sodium borohydride will reduce this ketone to the corresponding hydroxyl function group. So this alcohol which is formed by reduction of this acetyl group, when this is reacted with PBr3 simple nucleophilic substitution reaction, we know alcohols, they are converted into bromides. So this will be converted into the corresponding bromide, and again when this is reacted with sodium cyanide, again cyanide will act as a nucleophile and nucleophilic substitution reaction will take place. This nucleophile will attack this carbon and Br will be removed and the corresponding nitrile derivative will be formed. And when we hydrolyze this nitrile under acidic medium, this nitrile will be first converted into amide, and then amide will further hydrolyze it to carboxylic acid, and we will get phenoprofen as the product. So this is how in a 5-step process we can synthesize phenoprofen from bromobenzene and 3-hydroxyacetophenone. The next is ketoprofen. Ketoprofen again is synthesized from this benzophenone derivative. So 3-methyl phenylmethanone, basically this is benzophenone, and we can say 3-methyl benzophenone is used as the starting material for synthesis of ketoprofen. So most of the reaction will take place at this methyl function group modification reactions. In the first step, this will undergo reaction with bromine. So bromination will take place at this carbon. This will be converted into the methylene bromide. Then this alkyl halide will react with sodium cyanide, again nucleophilic substitution reaction. Na from here, Br from here will be NaBr will be removed, and this carbon will get attached with cyanide group or nitrile will be formed. The corresponding cyanomethyl benzophenone is formed. Then this cyano group, cyanomethyl benzene, when reacted with a strong base like sodium ethoxide in presence of diethyl carbonate. Uh, Basically, in the first step, this base will react with will abstract one of the acidic protons. These protons are acidic because of the electron withdrawing nature of this nitrile group as well as the aromatic ring. So this carbanion will then attack this carbon of the diethyl carbonate, and the corresponding ester will be formed. Then this you can see that this is electron withdrawing group, this is electron withdrawing group, this is electron withdrawing group. So this cyanoesteric ester derivative is having this proton which is even more acidic. So when this is reacted with methyl iodide, then this will act as a carbanion, and I from here, H from here is removed, Hi, and methyl will get attached to this carbon. So C methylation will take place through nucleophilic substitution reaction, and this H will be converted into methyl group. So we will get this type of product. So now we are having methyl group, cyano group, and ester group, and we know if we hydrolyze this in acidic medium, then this will be hydrolyzed to carboxylic acid, and this will be leaving as HCl, and we will get this ketoprofen as the product. So this is how ketoprofen can be synthesized from benzophenone derivative. Then next is pyroxicam. Pyroxicam is basically a derivative, is synthesized from saccharin. This is saccharin, and saccharin in turn is synthesized from toluene. So when toluene is reacted with chlorosulfonic acid, we will get 2 toluene sulfonyl chloride by this reaction. On reaction with basically sulfonation of the benzene ring take place at the ortho position. Then this sulfonyl chloride will be converted into sulfonamide when this is reacted with ammonium. So toluene sulfonyl chloride is converted into toluene sulfonamide, and then this toluene sulfonamide on oxidation is converted into saccharin. So basically what happens is that oxidation of this methyl group take place. So methyl is oxidized to carboxylic acid, and then OH of the carboxylic acid and H of this NH2 water is removed, and cyclization take place, and we will get this type of product which is called as saccharin. Now saccharin, when this is reacted with sodium hydroxide, the sodium salt of this saccharin is formed, and this sodium salt of saccharin on reaction with methyl chloroacetate, basically what will happen, this nitrogen will act as a nucleophile, will attack this carbon with the removal of Cl from here. So NaCl is removed, we will get this type of saccharin substituted acetic acid methyl ester. So N substituted acetic acid methyl ester is formed. Then this methyl ester reacts with sodium methoxide using DMSO as a solvent, and ring expansion will take place with this CH2 acting as a carbanion, and this will attack this carbon of the carbonyl, and this carbon nitrogen bond will break and ring expansion will take place, and we will get benzothiazine derivative. So this 1,1 dioxide 3 methoxycarbonyl 3,4 dihydro 2H1 2 benzothiazine 4 on is formed as the product. Then this benzothiazine derivative will react with methyl iodide, so N-methylation will take place. So N-methylation, N-methylated product will be N-methylated benzothiazine 4-on will be formed. Then this N-methyl benzothiazine 4-on will react with the 2-amino pyridine, and this will add to this carbon with the removal of methoxy from here, H from here, methanol will be removed, and CONH bond will be. So this is how pyroxycam can be synthesized. You can say from saccharin or toluene, starting from toluene. And again, this is an antipyretic compound. Then another commonly used antipyretic compound is indomethacin. Indomethacin is basically an indole derivative, and this is synthesized by Fischer-Indole synthesis, which is very commonly used in heterocyclic chemistry. The starting material is methyl 4-oxopentanoate. When this is reacted with this phenylhydrazine derivative, 4-methoxyphenylhydrazine, and we know that this will phenylhydrazine, they will react with carbonyl compound and undergo condensation reaction, and the corresponding phenyl hydrazone will be formed. So this hydrazone derivative then undergoes Fischer-Indole synthesis to give us indole rings through cyclization process. So we will get these types of methyl esters of 5-methoxy-2-methyl-3 indolyl acetic acid. And when these methyl esters of indole derivatives, they react with sodium hydroxide, hydrolysis of this ester functional group will take place, and these will be converted into carboxylic acid. Then these carboxylic acids, we will protect this hydroxyl function group of the carboxylic acid using tertiary in presence of dicarbodiamide, dicyclohexyl carbodiamide in presence of zinc chloride. This will give us tertiary butyl group substituted with hydrogen. So this is acting as a protecting group for this carboxylic function group, so that the reaction could not take place on this hydrogen. So this is function group protection. Then in the next step, when this indole derivative is reacted with 4-chlorobenzene benzoyl chloride, 4-chlorobenzoyl chloride, basically this will act as a nucleophile and attack this carbon. Cl from here, H from here will be removed, this will get attached to 4-chlorobenzoyl chloride will get attached to this hydrogen. So an acylation basically will take place at this step in presence of a strong base like sodamide in DMF. Then at high temperature, this protection which we have given in this step can be removed very easily under ST conditions, and the acid group will be generated back. And this is how indomethacin can be synthesized from hydrogen derivatives and ketones as the starting materials. Then is next is Salendac. Salendac is again synthesized in a multi-step fashion, and here the starting material is 4-fluorobenzoate. This is synthesized through simple organic function group transformations. We know aldehydes when reacted with anhydride derivatives, for example, when this is reacted with propionic acid anhydride in presence of sodium acetate, the condensation between this and this propionic acid anhydride will take place, and we will get 4-fluoro-alpha-methylcinamic acid as the product. So this is a very common organic function group transformation synthesis of cinamic acid derivatives from aldehydes or ketones. Then reduction of this carbon-carbon double bond will take place when we react this with the hydrogen in presence of palladium and carbon. Palladium on charcoal, then this carbon-carbon double bond will be converted into carbon-carbon single bond. So the unsaturated carboxylic acid, that is cinamic acid, is converted into this type of saturated succinic acid derivative. Then when this succinic acid derivative is reacted with polyphosphoric acid, then cyclization will take place at these positions. So we will get these types of 1-indenone derivatives, 6-fluoro-2-methyl 2,3-dihydro 1H-indane 1-one will be formed as the product. And when these indenone derivatives they are reacted with cyanoacetic acid, we know cyanoacetic acid is a methylene compound where these protons attached at the methylene group, they are very acidic in nature, and they will form a carbanion and attack this carbon of the carbonyl, and basically Michael addition will take place at this, and we will get these types of indenone acetic acid derivatives as the product. So basically we will get 5-fluoro-2-methylidene 3-acetic acid as the product. And when this is reacted with N-mercaptobenzaldehyde, this one normal mercaptobenzaldehyde in presence of sodium methoxide as the base, basically this aldehydic function group, and this is methylene function group. CH2 from here, oxygen from here, condensation will take place, and we will get this type of indene acetic acid derivative is formed. And then oxidation of this sulfide to sulfoxide will take place when we treat this unsaturated indone acetic acid derivative with sodium periodate. This sulfide will be converted into sulfoxide. which will lead to the formation of silendac. So this is how silendac can be synthesized from 4-fluoro-benzaldehyde as the starting material. The next is diclofenac. This again is very commonly used. Even you must have taken it many times during infections and other types of analgesic and antipyretic diseases which may have taken place. Now, this diclofenac can be synthesized when the amines, aromatic amines, they are condensed with aromatic carboxylic acid. So when 2-chlorobenzoic acid is reacted with 2,6-dichloroaniline, we know that here under basic condition in presence of copper metal, this will undergo nucleophilic aromatic substitution reaction. So Cl from here, H from here, we will get these types of anthranylic acid derivatives. This is basically a substituted anthranylic acid is formed. Then this anthranylic acid derivative, when reacted with lithium aluminum hydride, basically reduction of this carboxylic acid group will take place, and this will be converted into the corresponding primary alcohol. So this primary alcohol will be formed. Then this reduced anthranylic acid derivative, when reacted with thionyl chloride, we know this is again a aliphatic nucleophilic substitution reaction. So OH will be replaced by chloro group. So the corresponding alkyl chloride will be formed. Then again this will undergo nucleophilic substitution reaction. This will act as a nucleophile, attack this carbon, this will be removed, Cl from here, Na from here, NaCl will be removed, and Cn nitrile will get attached to this carbon. We will get the corresponding cyanide, benzyl cyanide will be formed. Then this benzyl cyanide, when this undergoes hydrolysis in presence of sodium hydroxide, nitrile will be first converted into amide, and then further hydrolysis of amide will take place to give you carboxylic acids as the derivative. So this is how these condensation of aromatic acids with aromatic amines will lead to the formation of diclofenac as the product. And in the market, this is generally sold as sodium salt. So sodium diclofenac sodium we say. Then is phenylbutazone. Phenylbutazone is this type of organic compound, and this is synthesized starting from aniline. When aniline undergoes diazotization reaction in presence of NaNO2HCl, this will be converted into phenyl diazonium chloride, and this will undergo then coupling reaction to give you this diazo compound. This on reduction will give you this reduced dinitrogen compound, and when this condenses with this diester, this nitrogen will attack this carbonyl, OT will remove OT from here, H from here. Ethanol, similarly one molecule of ethanol will be removed from here, and we will get phenylbutazone as the product. So this is a very simple process of converting aniline and diethyl malonate into phenylbutazone as the product. Then similarly we can synthesize oxyfen-butazone also. Only difference is here the starting material, where for diazonium coupling in case of phenylbutazone we have used benzene, here we are using phenol. So we will get this derivative as the phenol. So only substitution is different. Than this will react with benzyl bromide to give us this ether derivative, benzyl ether derivative. Rest of the steps they are same as we have seen in case of phenylbutazone. So reduction will lead to formation of this, and then this will undergo condensation reaction of with this diester and oxyfen-butazone will be formed. Similarly, another method is that we can start with this compound. You react with benzoyl chloride, you will get this type of ester derivative. Then this ester derivative having these two nitrogen will again condense with diester, we will get this thing. Then hydrolysis of for this ester under acidic or basic medium will lead to the formation of. The next is Zompirac. Zompirac, this can be synthesized from enol of diethyl 1,3-acetone dicarboxylate. This as the starting material. So when this is reacted with methylamine, we will get uh, this primary amino group will attack this carbon. OH from here and H from here will be removed, and we will get N-methyl derivative of acetone dicarboxylate. And this whole process is called as Hence pyrrole synthesis, because Zompiriac is having a pyrrole function group attached in the ring. So this when reacted with acetyl chloroacetone will give us this type of diethyl 3-methyl 2-oxopropylamino-pentene dioate. This diester is formed. Then this undergoes cyclization through this condensation. This will attack this carbon. O from here and H2 water will be removed, and we will get this type of pyrrole ring synthesized. Then this pyrrole diester undergoes hydrolysis and decarboxylation of one of the ester group, and we will get this diester converted into monoester, and then this monoester undergo Friedel-Crafts acylation in presence of 4-chlorobenzyl chloride and anhydrous aluminum chloride. So at this two position of nitrogen, there will be acylation taking place, and then with sodium hydroxide, hydrolysis of this carboxylic ester group to the carboxylic acid will take place. So this is how this diethyl 3-hydroxypentene dioate is converted into Zompirac as the product. So these are the references which have been used for preparing this lecture. Thank you very much.